Hello, everyone. So this is the very last video, the 10th video in our series on the reactions of Chapter 8. It's been a long time coming, but this is the very last video. So I'm glad that you're here with me in this video. We're going to be talking about oxidative cleavage in this one. And oxidative cleavage is done two different ways. So one way is with hot basic potassium permanganate, which we will talk about. And the other way is with ozonolysis. Okay. And we're going to talk about the mechanism of ozonolysis, even though it's not vital. I think that it is important to know. And but we're not going to talk about the mechanism of hot basic potassium permanganate. Okay. So let's get started here. So I'm going to do hot basic potassium permanganate first. And you know what, we'll call this oxidative cleavage. And then we will do it with hot basic potassium permanganate. So potassium permanganate is KMnO4. Okay, so oxidative cleavage with hot basic potassium permanganate. So what this does is takes a alkene and cuts it in half. Okay, and I don't want to start with a ring, actually. Let's start with this instead. Yeah, this is a good one to start with. So we'll start with this one. And what we do is we put in KMnO4 with NaOH, water, and heat. Okay, so hot and basic potassium permanganate. Okay, so now what this does is I'm going to draw this down here. Okay, is we take the double bond. So this is where the double bond is, right? And I cut it in half down there. Okay, so if I cut this in half, then what do I get? Well, I get this, and then I also get this, right? Now put an oxygen at the end of each of those, and we're done. So this is the product. So I get this, and I also get this. So acetone, and then I get 1, 2, 3, 4. I get this butanone compound, okay? So I get 2 ketones from this, all right? So this is really all this reaction is. There's some caveats to it, though. And I also want to say that usually, and I'll write it down here, sometimes it's written like this. Sometimes it is written like the way that I'm about to write it, which is like this. So what I'm going to do is take one of those methyl groups off, and we're going to see how that's going to change the product. So sometimes it's written as 2 steps. So first step is KMnO4, NaOH, H2O, and heat. And then second step is acid, H3O plus. Okay. So whenever I cleave this double bond now, I get this, and I also get this, right? So this ketone is going to stay. But you'll notice that this is an aldehyde, right? I have a hydrogen here. This is an aldehyde. So hot basic potassium permanganate is a very strong oxidizing agent. So what it's going to do is it's going to take this hydrogen and oxidize it further into an OH. So I don't get an aldehyde in this case. I get a carboxylic acid. So this is going to get oxidized into a carboxylic acid. Okay, so we have a ketone and a carboxylic acid. All right. So let's scroll down and do another one here. And that only happens whenever I get an aldehyde with hot basic potassium permanganate. There is a way to only get aldehydes, which is ozonolysis. We will talk about ozonolysis shortly. So now let's take a look at a ring. A ring is sometimes complicated for some people, so let's take a good look at it. So what we need to see here is that whenever we break this bond, we still add the oxygens, but we need to make sure that the if we form an aldehyde, that we actually oxidize it into a carboxylic acid. Okay, so what I'm going to do is I'm going to scroll down just slightly more, and then break this ring. I'm going to draw it very exaggerated so we can tell exactly what's going on. So we have oxygen, oxygen, and then this is an aldehyde, right? So again, this is going to get further oxidized into this, but the ketone stays, right? So ketone stays. So then this aldehyde is going to turn into a carboxylic acid. Okay, so this is my product, all right? But it's weird to write the product this way. No one is going to write it like this. So you should write it linearly. So I have 1, 2, 3, 4, 5, 6, 7 carbons. So 1, 2, 3, 4, 5, 6, 7. And then I have my ketone here, and then my carboxylic acid is here. Okay. So it takes this ring and it turns it into a completely linear molecule. All right. So I take the ketone and I have a carboxylic acid here. All right. And if I didn't have this methyl group here, like if I just did cleavage on this, if I just did cleavage on this one, right? So under the exact same conditions, so KMNO4, NaOH, water, heat, and then acid, then I would just get 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I'd get a double carboxylic acid on each side. Okay, so double carboxylic acid there. So this is really all the caveats for this one. There's one other thing that I do want to mention though that is important. All right, so I'm gonna come back up here and erase some of this. That way I have a little bit of room. So the thing that I want to mention is that all these alkenes that we have been doing are alkenes that are not terminal. Okay, so what I mean by terminal is if I have an alkene like this. So now if I have this alkene and I put it through hot basic potassium permanganate, something a little interesting happens. And we'll do 2 examples with this. So NaOH, water, and heat, and then 2 is acid, right? Okay, so I'm going to cleave the bond here, so that's no problem. So I get this ketone, right? Because I cleave the bond there. So whenever I cleave this, I get this, but then I also get what's at the end of this? Well, the end of this is just a carbon with 2 hydrogens, right? So I get a CH2. Okay, so I get this and a CH2. So this gets an oxygen and turns into this ketone, right? But if I put a double bonded oxygen on CH2, let's see what that looks like. So CH2 double bonded oxygen. Okay, so I put a double bonded oxygen on CH2. You'll see I have a hydrogen here and a hydrogen here that can both be oxidized. So that happens. So these get further oxidized. So I get like 2 hydroxyl groups on this, as well as this carbonyl group. Okay, this is very unstable. This does not exist for long. This decomposes into CO2, which CO2 looks like this. This is what CO2 looks like, C double bonded to 2 O's. Okay, so anytime, what I'm trying to get across is that anytime I have a terminal alkene like this, and I cleave it with hot basic potassium permanganate, I get this, and I don't get CH2, I don't get this, I don't get this, I get CO2. Okay, so let's do one more example with that. Let's do this one. water and heat. And then as a second step, I just add my acid in. Okay, so then if we cleave this right here, right? If we cleave this bond, let me erase this stuff down here so that way it's not in the way. So if I cleave this bond, then I get this, but this has a hydrogen on it, right? This is an aldehyde, so that hydrogen's going to get oxidized into a carboxylic acid. So I have 1, 2, 3, 4. 1, 2, 3, 4. So that's an OH. This is one product. And then remember, my other product is that I have this, and then both of these get oxidized, and then it breaks down over multiple steps into CO2. So my other product is CO2. So anytime I have something terminal like this right here, I'm going to get CO2 with hot basic potassium permanganate. Whenever I use ozonolysis, it works differently. Okay. So this is pretty much everything about hot basic potassium permanganate. So now let's talk about this. Let's talk about ozonolysis. So with ozonolysis, you'll remember with the last one that I was unable to get aldehydes because aldehydes oxidize into carboxylic acids. With ozonolysis on alkenes, I never get a carboxylic acid. Okay, that never happens. So let's take a look at this one. We cleaved this one earlier. And so with ozonolysis, my steps are, first step is O3, which is ozone. And my second step is CH3 2S. This is dimethyl sulfide. Okay, so dimethyl sulfide. So ozone with dimethyl sulfide. So again, I cleave the bond right here, and then I just add an O. Okay, so my first one is going to look like this, right? I have a hydrogen here, and then my other one is going to look like this. So you remember with the other one, I have this H here that would have oxidized into a carboxylic acid, but in this case, it doesn't happen. So I'm left with the aldehyde. The aldehyde stays. So I get this, and then I get the other thing that I wrote there. So I get both of these as products. Okay. So I don't have to worry about potentially making carboxylic acids with this one because I can't. With alkynes, it's a completely different story, but with alkenes, I don't make carboxylic acids. Okay. One other thing I want to mention is that typically this is at a very low temperature. So like we're talking negative 78 C, something like that. Usually it has to be very cold in order to work well. And the only thing is that I'll say is that I could also use, for a second step, I could use zinc and acetic acid. So it's ACOH, which is acetic acid. So I could also use zinc and acetic acid. I just prefer dimethyl sulfide because we're going to be doing the mechanism later, and I'm going to use dimethyl sulfide in that mechanism. So, okay, let's do this with a ring, and then let's do this with the terminal alkene, and then we'll talk about the mechanism. So with the ring, we'll do this same ring that we did earlier. So again, first step is O3, second step is dimethyl sulfide, and this is dimethyl sulfide, so it's an S with two methyl groups on it. Sometimes it's written that way. So again, I cleave the ring, and then I get this and this, but I have a hydrogen here, but remember this doesn't oxidize with ozonolysis. So this is 1, 2, 3, 4, 5, 6, 7 carbons, and I do not get the carboxylic acid in this case. So 1, 2, 3, 4, 5, 6, 7. So now I'm just left with my aldehyde, not a carboxylic acid in this case. All right. So very last thing that we'll mention is that if we have a terminal alkene like we had earlier, so we had this one, right? So with potassium permanganate, since it's such a strong oxidizing agent, it fully oxidized the CH2 that we get into CO2. But in this case, that does not happen. So I break this bond, right? So I get this, and then I also get my CH2, which turns into this, right? So CH2 double bond O. This is formaldehyde, and ozonolysis keeps this as formaldehyde. This does not change. Okay, so it doesn't get oxidized any further. So in this case, if I have a terminal alkene, I get this same thing, but then I also get formaldehyde, which with the other one, it would be impossible for me to get formaldehyde because I would just immediately get that oxidized into CO2. Okay, so with this one, it's actually possible for me to get formaldehyde. All right. Okay, so now I want to very quickly talk about the mechanism of this one. This mechanism is not vital by any means, but I do think that it is good to know for sure. So I'm going to erase this and then we'll talk about this mechanism. For ozonolysis, that is. Mechanism for hot basic potassium permanganate, we're not worried about. Mechanisms with metals are usually hard to know. Like sometimes they don't even know what they are, and other times they're just very complicated. So we'll save ourselves some trouble and not worry about it. Okay, so I'm going to do ozonolysis on this one. This alkene. And then as a first step, I'm going to put in O3. As a second step, I'm going to put in my dimethyl sulfide. I keep on saying dimethyl sulfoxide, but it's not. So then my two products are this and this. That's what I get as my two products. All right, so I get two ketones from this one. So let's take a look at this mechanism. So I'll draw this out first. Okay, so now I'm going to draw ozone. So ozone looks like this. So this has a plus charge on it, and then this oxygen has a minus charge. So I have a positive and a minus all in the same molecule, and I have this double bond as well. So I have a lot going on in ozone, honestly. So this negative charge is going to act as a nucleophile, and it's going to attack the double bond, and then the double bond is going to attack the other oxygen, and then these electrons are going to go on to this oxygen to get rid of that charge, that positive charge that's on there. Okay, so now this makes a pretty interesting intermediate called an ozonide. So let's see if we can kind of decipher what's going on here. So this is going to be the bottom of my intermediate. So this carbon over here has two methyls on it. This carbon here has a methyl and an ethyl, right? So I have methyl and an ethyl, two ethyls. So the ozonide forms between this carbon and this carbon, all right? So now my ozonide is going to look like this. So I have three oxygens in this ring, okay? And each oxygen has no charge, and they all have two electrons now, okay? Because one pair of this electron, one pair from this oxygen formed this bond, so now it only has two electrons. Another pair got donated here, but this one already had two, so then a pair left, and that pair formed a, or that those electrons in that double bond formed a lone pair right there. Okay. So this is my ozonide. All right. So it's ozonide. And so these oxygen-oxygen bonds are unstable and they do not like to exist for very long. So what is going to happen is there's going to be a lot of electron pushing that's going to get this to not exist anymore. So these electrons are going to go down here and make a double bond. So that's going to give this carbon here too many bonds. So this carbon, or this bond, excuse me, is going to break and those electrons are going to form a double bond here with this oxygen. And then finally, that's going to give this oxygen too many bonds. So these electrons are going to go on to this oxygen. And this happens spontaneously because these oxygen-oxygen bonds are unstable and they don't really want to exist. So the one thing that I form is a ketone right here. So I have two methyl groups on this carbon, and then I just formed a double bond with this O, right? So I'm making this ketone. Let me write what I'm making right here. So I'm making this ketone, okay? And this is being formed from this bond breaking, right? And then so I just have the two methyls, and then these electrons go here to make this double bond. Okay, so that gives me this ketone. The other thing I form is, this has a methyl and an ethyl on it, right? So methyl and ethyl. And then I have these electrons here came down to make a double bond with the O, but then this oxygen is still bonded to this other oxygen here. So now I have this. Okay, so I have this and this. These are the two things that I'm forming. Okay, so I just kind of wanted to explain that before I drew it. I'm going to draw this ketone upside down for a important reason we'll see in a second. So we get this ketone, and I'm going to erase these. I just wanted to explain that for some clarity there. So we get this ketone, and then the other thing we get is this with this oxygen on it that has a negative charge. Okay. And the oxygen, this double bonded oxygen here, is positively charged as well. Forgot to mention that. And that's positively charged just because I just lost an electron pair here, so it only has one electron pair, and then it has 3 bonds. So 1, 2, 3, 4, 5. So 6 minus 5 is plus 1. So the formal charge on this is plus 1. Formal charge on this one is minus 1. So again, this thing is not great. It's not very stable, right? So it doesn't really want to exist. So what happens is this is going to act as a nucleophile on this, okay? And that's because this carbon-oxygen bond right here is polar, right? So this carbon is slightly positive and this oxygen is slightly negative. So since this carbon is slightly positive, then these negatively charged electrons are going to be attracted towards that slightly positive oxygen. Okay, so at the same time, though, since I'm forming this, these electrons in this double bond have to go somewhere. So these double bonded electrons are going to go to this carbon. Okay, which means these electrons had to go somewhere and they're going to go onto this oxygen. Okay. So now I have formed a real animal here. So what I've formed is, I'm trying to think about the best way to draw this. Yeah, probably. So these are my two methyl groups right here, right? And so this carbon just bonded to this oxygen here, which now has 2 lone pairs. And this carbon was already bonded to this oxygen here that has 2 lone pairs, right? So this carbon is bonded to the 2 oxygens. And then this oxygen, because we use these electrons in this double bond to attack here. So that means this oxygen is going to be attached to this carbon right there. And then this carbon is the one that has the ethyl group and the methyl group on it, right? And then finally, this one is attached to this oxygen, which also has 2 lone pairs on it because we just gave it another lone pair. And then this was already attached to this to begin with, right? So this is another ozonide that I get, okay? So this is my secondary ozonide that I form. Okay, so now whenever this forms, the dimethyl sulfide that I have in here is going to come in and it's going to do its job. So dimethyl sulfide looks like this. I keep wanting to say dimethyl sulfoxide, sorry. So it's dimethyl sulfide. Okay, so dimethyl sulfide is going to come in. And again, this oxygen-oxygen bond, I only have one oxygen-oxygen bond, right? The oxygen-oxygen bond is unstable and it doesn't want to exist. So it's going to come in and it's going to attack this oxygen. So that way that oxygen-oxygen bond can stop existing. So then these electrons are going to go down here to form a double bond. So that way I can form one of my carbonyls, right? Because I'm forming two carbonyl groups. So that's going to form one carbonyl. And then these, since I just formed a double bond here, this bond has to break. So these electrons are going to go here to form my other carbonyl. And then this is the last arrow, I promise. These electrons are going to go here onto this oxygen because this carbon just is gaining another bond, right? So this bond has to break, okay? So then this is going to give me my final product. So I just formed a double bond here with these two methyl groups. The carbon that has these two methyl groups on it just got a double bond O. So that's one of my products. And then my other product also formed. So I have this carbon that had the methyl and the ethyl on it. This just formed a double bond O as well. Okay, so I just formed another double bond O here with this carbon. And then my byproduct, you'll notice, is this. So it's the dimethyl sulfide with one electron pair, and the sulfide has a positive charge. And then this oxygen has three lone pairs. It has a negative charge. So this is because I already had two on there, and then it gained another one. So it has three lone pairs. So if you take a look at this and we draw a resonance structure of this, put those electrons down there, what do we get? It's a full circle moment here. We get, whoop, we get this. So if you don't recognize that, that's dimethyl sulfoxide. That's DMSO. So we form DMSO as a byproduct of this, okay? So, but byproduct isn't super important. I just think that it's interesting that we form DMSO in this reaction. But the important thing is that we have a lot of electrons moving around, and we form the ozonide, and then we have more electrons moving around and even more moving around. And then we finally get to our two carbonyl groups as our product, okay? And, we would just form an aldehyde if, I was missing one of these methyl groups or something like that. So all good. So hopefully this was helpful. Like I said, this is the very last video in our series on chapter 8. So hopefully all of these videos have been helpful. And I will see you in the very first video on chapter 9, which is going to be addition of HX to alkynes. So hopefully you'll join me for that one, and I will see you later.